Welcome. Thank you for joining for yet another session on embedded software and system development. I will take a short look back. I'm really happy that we are having this series together with Thomas Schütz from Protos Software GmbH. And we started about 2 months ago with architecture-driven development of embedded software systems. And this live event we are still providing on the same YouTube channel. Then the next event was how can I test my embedded system during development? And the topic today is continuous integration for embedded system. And as I said, I'm very, very happy and grateful that Thomas Schütz from Protos is joining us and is providing us with his deep technical know-how and insights and sharing his know-how with us and you. Welcome, Thomas, and thank you for joining us.
Thank you, Annette. Happy to be here again. The topic today is continuous integration for embedded systems. Why is it so difficult? What is different than, for example, for a normal software system and so on? So let's have a look at the motivation. So why do we want continuous integration? What's one of the basic problems here? One of the biggest problems is that the testing of an embedded system gets more and more expensive in the process. So at the beginning, you start with the implementation, you have unit tests. That's fast, relatively easy to do, good to automate, and so on. Later, you make some integration tests, some system tests, and you see the effort gets much, much bigger, and the return time, the cycle time for testing gets much, much longer. So what we want to do is what we need to do is to bring all those test stages as near as possible to the development. So if you run a system test, I don't want the system test to run every couple of months by getting into a car and driving around the corner. But I want this completely automated and as fast as possible after every change. So we're talking about minutes, maybe half an hour reaction time, a turnaround cycle for a test of a system after every software change, for example. So we need to learn and test earlier. That's the biggest topic here. So let's have a look at the typical development process for an embedded system. You probably start on an evaluation board already with the right target processor. You commission your drivers, you configure your drivers, you create hardware-related software components, motor controllers, battery control, bus systems, bus protocols, and so on. On top of that, you have your software components, you integrate everything to an application, and eventually you should start to test something. So where does this happen? Usually the unit tests focus on the software components because it's really hard to test, for example, a motor controller or drivers or the like with a unit test. So the main focus here is software components, maybe even not all the software components, if it's asynchronous, concurrent, and so on, what's very typical for an embedded systems. That's hard to do with a unit test. Later, you can use a kill test system on system level, for example, for a test, and or even run a real system test, so not a simulated system test, but a real system test with the real hardware. Usually those two steps are really way back in the development process, so they are very late, and they're usually pretty expensive, and so they do not run very often. And you can see we have a lot of white space here where the developer actually maybe can try out things, but that's not a structured way to test. It's not automatable. It's not repeatable, and so on. And it's far from being complete. So what we did is with the Minihill, we provide a hardware-software integration test solution on the target processor but a hardware in the loop test system where you can test actually the complete software stack on the right target processor. So that's the precondition for what I'm going to explain now regarding continuous integration. So again, what do we really want and need? The most important thing here is we want to test what has changed most frequently, and that's your software. It's not the hardware. So hardware in the loop is not necessarily about testing hardware. You can use it to test hardware, but you don't need to test the hardware if you change it every 5 months or every couple of weeks or something like that. But the thing you change most frequently is your software, maybe 10 times or 100 times a day. You have 100 commits a day in a big project. That's quite normal for a bigger embedded software. Even if you work alone, you might have, I don't know, 5 or 10 commits a day. So you want to change the software and you want to test the software. So every code change of every developer needs to be or should be tested within minutes. Why within minutes and not within weeks or months? After 5 minutes or after half an hour, you still know what you changed. So you need to know very fast, because if you still know what you changed, you're probably the only one that changed something within the last 10 minutes or so. It's really easy to fix the bug if you detect it immediately. After a couple of months, you might have a couple of 100 commits by dozens of developers on the same project. It's really hard to localize a problem. Then what's also really good to have is a full regression test, also for unrelated code. Because in an embedded system, it's even worse than in a normal software system. You have a lot of side effects. You have memory leaks, you have shared resources, and so on and so on. So you change something over there, and over here, something happens. So you need to test not only what you change, but also all the other stuff that's related somehow, because it's running in the same environment, in the same processor, and you have shared resources. So the next thing you want to have is continuous integration for full test automation to enforce tests. So you do not get around the tests. No developer gets around those tests. And he even saves time because it doesn't have to execute the tests. It's done automatically. So that's continuous integration. And if we're talking about embedded systems, it's really useful to have an automated hardware in the loop test, because we want to test more than pure software units. So if you're only interested in unit tests for normal software, you can stop now. But if you're doing development for embedded systems, you should listen a little bit more, maybe. So why do we want continuous integration? Let's have a look at the typical integration problem. So let's say we have an integrator. This can be a team, this can be one person, this can be a technical solution, whatever it is. And developers start to develop things. We have the first developer with 20 changes, then next developer with 50 changes, 30 changes. And suddenly you have a developer that developed for, I don't know, months maybe, and is committing all the changes at one time, or pushing. So the integrator already gets in trouble here, and he receives more and more changes and needs to integrate and test them maybe. And that's integration hell. That's the saying for it. And that's a very typical situation, because all those changes are done usually or committed usually and integrated very late in the process, because everybody is working in his bubble, doing his changes, his new features. And you see all the other developers are happy because they know their stuff works, but the integrator has the trouble here. And that creates a really big trouble. And I guess you all know the situation. So how does continuous integration work to help here? So we still see the happy developers, and we see the continuous integration server. In this case, the logo of a Jenkins server. Doesn't really matter what it is. Can be a GitLab, GitHub, Jenkins, Azure, whatever you take is good. The important thing here is every commit in the source code management system, for example, a Git, triggers automated build automated tests, and potentially automated releases. That's very important because every commit is tested. So you get an answer after a couple of minutes, maybe from the test system. Some best practices here are every change is integrated and tested. So every commit is tested. Then another thing that's important is early and often. So you commit early, you commit often to fail fast. If you wait with your commit for 2 months, the continuous integration doesn't help you. But if you commit, for example, you make a bug change for a couple of hours, create a little test case for that, then you commit it, and the continuous integration server runs on the commit, test this, that helps a lot. So fail fast. If you want fail fast, you need to commit early and often. And by doing that, the bugs can be detected and fixed very early, sometimes within minutes. And it really works extremely well, especially in non-embedded software, because there you only have software tests. That works a little bit easier than for embedded system, but it also works for embedded systems. So now some rules and principles for continuous integration. Quality equals speed, and speed equals quality. So that means if you have a high quality production, you're gaining speed in the development speed. So you're faster in developing your software. If you're faster in development, you can focus more on quality. And continuous integration helps with both. It helps to speed up your process, and it helps to improve your quality. And that's a really nice thing to have. So commit early, commit often. I already talked about that. Then never commit broken code. Why is that? If you commit broken code, your software cannot be built. If it cannot be built, it cannot be tested. So you invalidate the continuous integration. It's worthless for the next commit. So the rule here is also fix build problems immediately, because you want the continuous integration to work for the next committer. So that's very, very important. Fail fast for fast feedback. If you have longer running tests, then split them up. Make staging on a continuous integration server. Build your pipeline in a way that the first stage builds and tests your software within, 5 minutes, 10 minutes, 15 minutes. And if you have long-running tests, performance tests, stability tests, and so on, stress tests, robustness tests, let them run overnight or over the weekend or every couple of hours. You have an automated build and test system, so split it up in the short-running tests and the long-running tests, so you get early feedback for 95% of the problems. That's very important. Another topic is act on metrics. So that means if you're already generating your software, your tests automatically, you can also generate metrics, for example, using a static code analysis, or also test coverage. So test coverage does not tell you that your tests are good or your quality is good. So it's not a quality metric. Be aware of that. Code coverage is not a quality metric, but it helps you to detect holes, gaps in your testing strategy. So you commit a new function. Let's say you create a new function or a new class or something like that, or a new C module. And the code coverage can tell you, okay, here you have a couple of lines or hundreds of lines of code that have not been touched by a test case. That's very useful. And then you can act on that. You can say, okay, now I have detected the problem here, so let's fill the hole. Then build for all the targets. If you're developing embedded systems, the chance is high that you have different targets. And so maybe you only test on one target, but build all the others. A compile run is essentially a static code analysis. So please do this as well, because then you can deliver the software also for the other targets. It's part of the test. And then last but not least, release and deliver always. So Why is that? Even if you do not release the software to your customer directly, just build and release the software always as if you would deliver it. Because then you know you can deliver it whenever you want. So the delivery process is, if it's automated, is also a part of your test process. That's really helpful. And for example, if your system test department says, okay, I need a stable version of the software, you run the continuous integration server and you deliver automatically to your system test department. They can flash it in the car and drive around the block or through the desert, and they know they have a complete working release as far as the continuous integration is concerned. So really helpful, speeds up the process by order of magnitude at this corner. Okay, so test automation is a precondition for continuous integration. Yes, you can run it also without test automation, but the biggest worth is, the biggest value is in the test automation usually. So let's have a look at the different test levels and methods you can use. Not all on continuous integration. Let's have a look at the normal ECU, electronic control unit with a microcontroller, with software units inside with the drivers. Then on the electronic control unit, you might have power electronics, sensors, actuators, and so on. And then outside your ECU, you have, for example, a motor, a pump, a hydraulic system. So that's the system you're controlling. And now you can test on different levels. Let's start with the unit test. Unit test and software integration test is usually pure software testing. So unit test is just testing one unit, so one C module, one class, or the like. Software integration test brings together more C units, more classes, and so on, integrates this. It's usually synchronous and step by step. So that's very good. It's good to have. You can test very deep, but it's hard to test asynchronous things like a motor control, concurrent systems, and so on. But we have an embedded system, so it's very likely that we have asynchronous processes. And we also have drivers that are part of our software. So the first step where you can actually do this is a black box test of the microcontrollers at the pins of the microcontroller on signal level, and that's the smallest possible hardware-in-the-loop test system. This would be the mini hill. That's the first step where you can actually test the complete software stack as it is, as it's delivered, including drivers, including your complete software stack. And you can test this completely as a black box. So the next step would be maybe a big hardware-in-the-loop test, including already the complete ECU, with power electronics, with sensors, with actuators. If you already have a temperature sensor on the ECU, you need a climate chamber. That's slow, it's hard to automate, and so on. So it's very useful. Don't get me wrong here. Hardware-in-the-loop test, a big hardware-in-the-loop test is really good because it's almost a complete system test. But it's slow, it's hard to automate, and it's expensive. And in the end, you run a complete system test. So you get into the car and drive through the desert, Nevada, for example, and that's obviously very expensive, and you cannot do this very often. And you cannot do this on every software change. So with respect to continuous integration, unit test, software integration test is really easy to automate with continuous integration. It's pure software. It runs basically anywhere. If you do not mess it up by using direct calls to hardware in your software modules and so on. But it's fast, often inexpensive, and so on. Then at the bottom here, you have a system test, hardware-in-the-loop test, the big hardware-in-the-loop test. That's usually very slow. It's expensive. You cannot run this very often. The resources are never free because they are so expensive. And it's really hard to automate with continuous integration. Imagine driving through the desert Nevada in your car to test your system. You cannot automate this with continuous integration. So, and right in the middle, you have the mini hill with the hardware in the loop test, the smallest possible hardware loop test. It's, of course, more effort than a unit test. but it's really good to automate, and you get response times in the range of minutes, and it's much cheaper than a big hardware in the loop test or a system test. So it's right in the middle there. Yeah, let's have a look at the typical continuous integration delivery pipeline. I've been talking about staging before. The typical stages, just as an example, could be commit stage. So in the commit stage, for example, you build your software, you run the static code analysis, you run the unit tests, software integration tests, so everything that's done with a unit test, for example. Then the second stage could be an acceptance test stage. In many cases, this goes together with the commit stage. You do not have to separate this if it runs very fast. Here you could run a hardware-software integration test, acceptance tests, and so on, automated acceptance test. Then the third stage could be a capacity stage, performance, robustness, safety, and so on. Sometimes in this stage, the tests run really, really long because you want, for example, have stability tests over a certain period of time, or make robustness tests, stress tests, and so on. They usually take a little bit longer, so put them in a separate stage. Then the next stage would be a user acceptance or a system acceptance test stage. So user acceptance test is usually a manual test. Software system test is usually an automated test, or can be an automated test. And in the end, you have the delivery stage. By splitting them up, you have a clear structure in your test process, and you do not have to run everything just to know a couple of errors or so. So that's for typical software systems. And by the way, the implementation effort goes from bottom to top. So to build static code analysis unit test is usually not much effort. User acceptance test, software system test is already a lot of effort, especially user acceptance test, because it's in many cases done manually. So if we have a look at the embedded systems, we can add a couple of more boxes here. So for example, in the commit stage, you could run a software in the loop test, model in the loop test if you're using, for example, a Simulink or similar tools. You could run a model in the loop test for stability of your motor control and so on. Really nice to have. Then processor in the loop. Processor in the loop is usually on the right target processor, but already still a unit test, for example, or a software in the loop, model in the loop test, but on the right target processor, but without I/O. That's processor in the loop. And then later you can run a system in the test as a hardware in the loop test, or a system test in reality. Now, a unit test framework can help you with unit tests, software integration tests, and processor in the loop. Those are the typical things you can do with a unit test. And with a mini-hill, for example, you can support, you can run hardware software integration tests, acceptance tests, capacity tests, and also the hardware in the loop system test to a certain degree. Maybe not the complete system, but a big part of it. So typical response time for those different test levels are usually for the component test, unit test, a couple of minutes. So you press the button and you get the answer within seconds, minutes, something like that. Integration test, hardware software integration test usually is not done. In most projects, I know it's not done. System test already is very slow, very seldom. And the acceptance test is usually on system test level. So it's also not very often. It's not running very often. So unit test tools are, you can use unit test tools for the component or for the unit test level. For the hardware software integration test, you can use the mini-hill. And here you are basically in the same reaction time range as a unit test. You can test your system within minutes. That's really nice to have. And here you see the mini-hill board. You can attach this also to the continuous integration server later. So speed is the message. We want to fail fast here, also with the hardware in the loop testing. How do we do this? We have a very simple hardware platform for hardware-in-the-loop tests. It's a small platform. I can show you that. It's I have here my demo system. So it's as big as a piece of paper. Focus is to test the microcontroller with the complete software stack as it is at the pins of the microcontroller, so on pure signal level. We connect all the signals of the pins over this patch panel with our test system. So the blue one is the test system. And so that's a standard evaluation board, for example, from ST Microelectronics with the right target processor. And here on this chip, we run three things. We have the access to the pins. So we need to bring the IOs into our test software. The signals, those are typical digital, analog, SPI, all the low-level bus systems, PWM. So the typical things you need to control a system. And the second level you need environment simulations. So if you can imagine here a system of Kercher, for example, they have they're testing a lot of different systems with the mini-hill. And they have, for example, a pump or a compressor in there. So there's a motor control in there. But if the motor is not attached, the system fails. So you need to simulate the motor instead of putting it, hooking up with a real motor. You use a simulated motor. And once you have an environment simulation for the sensors, for the motor, for the battery, or whatever it is, suddenly you can bring your system into any state you want just by changing your simulation. And it's still a hardware-in-the-loop test because you're accessing the pins of the microcontroller as electrical signals. So that's the hardware system, and on top of the simulation, you need test cases, of course. The test cases are not a problem. The environment simulation is usually the biggest effort. It's not as hard as it sounds, but it's a little bit of effort to create an environment simulation for your test environment. So how do we do this? We have a completely model-based approach for the I/O access, for the environment simulation, and for the test cases. So we develop structure and behavior for the simulation and for the tests as models. From those models, we generate C code, compile it, flash it, and we run it here on this microcontroller. It's actually a microcontroller Cortex M7. Why are we using such a small Cortex-M processor? Because it needs to be fast and deterministic. So if you want to simulate a motor controller or motor for a motor control system, you need 20, 30 kilohertz. And that's something you cannot do on your laptop, for example. If it's hardware in the loop, you need to have hard real time. So that's why we use a hard real time system here. And here you see on the right, we have a different processor. Here, for example, an Oryx from Infineon. Again, the patch panel, and here the test cases and the environment simulation. So when we run the simulation and the test cases, we get logs. We transform the logs into meaningful diagrams because as human beings, we understand those diagrams much better than a text log, for example. And then we learn and iterate. Now, typical hardware-in-the-loop system on your desktop looks like that. That's a typical start for one project, for example, or for one developer, or maybe smaller teams, and so on. But if your teams get bigger or distributed all over the planet, or if you have bigger projects, more projects, continuous integration might be a good option. So every code change triggers the build of your embedded system and the test on the mini-hill board. So for example, in this case, we have 8 different mini-hill projects in one rack. So every commit triggers the fitting project here, or maybe all the projects. If you change a basic software library or something like that, you might want to change your complete software projects, everything you have. And in the end, you can automatically deliver, and you have a very high quality to deliver because you already know that your software system plus the signals really work. So By doing this, we can test every code change for every developer, doesn't matter where he sits, in which country, for every project within minutes. Now my continuous integration setup for the demo I'm going to show you is, I have a laptop, I have a Minihill attached to the laptop. Then I'm developing simulation and test models based on our developer studio here. Then I commit the test cases or the simulations to Git source code management. It's also locally on my laptop to have a stable demo. If I don't have an internet connection, I still can run the demo. Then I have a continuous integration server also on my laptop, in this case a Jenkins server, but doesn't really matter which continuous integration server it is. It's triggered by the commit of the Git source code management. Then I build, or the Jenkins server builds, flashes, and runs the tests and generates the reporting. So that's the test development process. But now we want to develop application, not test cases, and it's just the same process. So the system under test, if anything is changed and committed to the source code management system, the Jenkins just builds the system under test, flashes it, and runs the test cases again. So if the test cases are changed, they're running against the last version of your system under test. If the system under test is changed, it's running against the test models. Yeah? So little demo I have here is BLDC motor controller on an STM32 processor, an ARM processor. It generates 3 PWMs, calls the motor simulation. The motor simulation generates 3 Hall signals as digital outputs. So it's really a closed loop simulation. So the system under test does not know that it's not a motor because it's a simulated motor. And then I simulate the temperature sensor, for example, to trigger problems, to trigger errors, temperature shutdown or something like that. And I control the speed over UART, could also be CAN, LIN, or whatever you have. So that's the demo setup. Now I'm going to switch to the development environment. I will just briefly explain what this is. That's a model-based development environment for the Minihill, component-based. So I'm double-clicking. Now I'm inside my demo. Everything inside this box here is generated, compiled, flashed, and runs. So what do I need? I told you before I need IOs. So those are the analog adapters. For example, I have here analog out adapter that corresponds with this cable here. So it's the digital analog output 1. So this must be the red one here, red cable. So and the digital out adapter UART. Then I have a PWM measurement unit, Hall generator for the signals of the BLDC motor, for the sensors, and here I have a motor simulation. So on top of the IOs, I have the simulations. Motor temperature is straightforward. Celsius converted in an analog output, 3.305 volt. Motor simulator, of course, a little bit more complex than a temperature simulation because it's closed loop. So in this case, it's a state machine. So if I get a new duty cycle, I calculate the speed, and I inform the Hall generator component that it shall generate the Hall signals now with a new speed. So Hall gen, I could set the new speed, I could change the direction, I could break the system by making the speed wrong or whatever I want. So there are a lot of possibilities to create failure injection. If you already have a simulation model, a Simulink model, for example, you can use the Simulink plant simulation you're using also to generate C code integrated instead of the state machine. You have a Simulink block in there. That works pretty good because you do not want to redo the motor simulation. So you can reuse existing models if they can generate C code, for example. So on top of that, I need test cases. So for the test case, again, I have another description language. It's specialized for test cases here. Here you can see, for example, we can create steps. So for example, I want to change the speed. So I send over the UART. I can send a new request speed command, and I get the answer that it's been received. Here you see the sequence diagram that's automatically generated. So whatever I change here is changed in the sequence diagram. So it's pure documentation for us so that we understand better what happens here. That's not very complex at the moment. Based on those little steps, they should be reusable. You can create bigger sequences or sequences. So for example, a sequence to test a little bit more here for the motor control. And then you aggregate more and more sequences to a test suite. And here you have a big test suite with all the test cases and all the steps that are executed. And that's the specification of the test case. So now we generate the code. We can do it directly from here. We can also do it from continuous integration or from a graphical user interface. For example, here we have a little graphical user interface. I can start the test run, and now I'm pulling a plug to introduce an error. Now I'm fixing this error again. As you've seen, the error has been detected. And here you see that we ran into a timeout. Let's have a look at this timeout. Here you can see in the background the development environment switch to the right line, activate motor control. That's exactly activate motor control, the step where it actually failed. So far for the mini hill and the manual triggering of tests, but we said we do not want to trigger the tests manually. We want to trigger them on every commit. So let's have a look at this. I have in the background a continuous integration server running. That's a Jenkins server. Here I have the build pipeline running for this project. So that's the motor control mini hill, and it's listening on the Git repository. So now let's have a look at what happens when I change something. Let's do this here to the left, here the one to the right. And now I'm going to change something in the system under test. So not the test system, but the system under test. It's just a little bit of C code with a motor controller. So I'm changing the duty cycle fixed to 20% instead of using the real value. So the motor is turning all the time with the same speed, or maybe with a speed that's a little bit wrong or whatever it is. So now I've changed this. I'm committing this to the Git repository. That's my Git plugin here. So let's call this bug. I'm committing this, and I'm switching back to my continuous integration server. Sorry. And here you see immediately the continuous just a second. Here immediately the continuous integration server was triggered and starts to build the software now. So here you see it checked it out. Now it's assembling the project. So it's generating the project. Now it's flashing. Here you see it changed here, the LEDs, and here now it's changing those LEDs. So it actually flashed the test system. It flashed the system on a test. Now you've seen it blinking. And now it's running the test. So it's running the environment simulation and the test cases. And now let's have a look at what happens. Let's see what it detects. Now we see that the continuous integration server has turned yellow here. So why yellow? Yellow means it has built correctly, but some test cases failed. So let's have a look at the last test results. So there are 3 errors. I could have a look at them now, but what's really interesting is, so now I know, for example, the demo integration test, something failed here. Let's have a look at the sequence diagrams. And now we are looking at the generated sequence diagrams, not from the specification, but from the actual test execution. So that they are the same sequence diagrams, but they are showing me what actually really happened. So here an expect failed. That's the first test that failed. I'm clicking on the diagram, and in my development environment, I get exactly the place where my reaction failed. So the actual speed was not between low and high, as I expected, between two values, because I put it statically to 20%. So obviously it did not react on speed changes. Yeah. Okay, so that was the demo. I hope you enjoyed the little presentation and the demo. If you have any further questions, don't hesitate to contact me or Annette. Yeah, thanks Annette for the invitation. Happy to be here always. And yeah, back to you.
Yeah, thank you very much, Thomas. I think it's really great to have your insights. And I think this is also giving an additional view on the portfolio of the Embedded Academy, because we're more in the electronics and electrical engineering and e-mobility topics. And you're covering exactly these areas in addition, which is architecture, toolchain, and the testing. So we are always grateful to have you here and thus to present additional content to our customer audience. I would also thank you, everybody who joined us today. We will be back after the summer holidays. I think it's okay to be on holiday in August, and we're planning another session in September. Thank you again, Thomas, and the audience. Thank you, and bye-bye. Have a nice day.
Bye.